then click the thing. Okay, so in 2008 or so, I was sitting in a hotel room in Paris with my family. And as you will do when you're on vacation in Paris, I was checking my email. And these three papers on the bottom came across for me to review. And these were three papers that detected an absorption due to hydroxyl water on the surface of the moon, which was a surprise to most of us in the lunar science, the remote sensing community, though it had been anticipated. We got a hot mic out there. Out there in Zoom land, you can press the mute button. All right, so where was I? Oh, okay. So these three papers reported detection of a 3-micron feature due to either water or hydroxyl on the surface of the moon. This had been anticipated by some laboratory experiments done even before Apollo, where bombardment of simulants by protons had produced OH in these simulated surfaces. Zeller et al. In 1966, those experiments, and there were half a dozen other experiments that showed this process should operate. But we remote sensing people don't believe laboratory experiments, and so we had to actually observe these. And this was coincident with the discovery of higher water contents by Sol et al. In the lunar samples, but that's interior water. We're talking about water that is exogenous to the moon. Let's see. Okay, one thing about the observations is that the previous slide made it look like there was a strong latitude component. That's actually an artifact of the M-cube data, which only observed at near a local noon. But we've observed this feature from the ground, and also the Deep Impact spacecraft shows that it's strongly temperature dependent. So the observations that we've done from the ground, we take profiles down the 0 longitude at different lunar phases. And so here's a plot that shows the intensity of this H2O absorption translated into parts per million of water as a function of latitude, and the scale bar up there is hours from local noon. So the curves that are towards the bottom, that sort of bottom out near 0, those are at those are at near local noon. The points that are at higher are farther from local noon. The next slide puts this actually in terms of local time. Oh, this next slide. Arrow meant something once upon a time. So here is in terms of local time. And you can see that you still have this, time of day superimposed at all latitudes. The point is here that this temperature feature is strongly temperature dependent. And this is actually kind of a puzzle from a spectroscopic point of view. We have not been able to identify any optical effect. So this must be something to do with the abundance of hydroxyl water in the surface. There are only 2 sort of surviving hypotheses. Just one other kind of cool observation we've done recently. We've measured the surface during lunar eclipse while the sun goes behind the Earth. So the temperature of the surface drops rapidly. And we found that at the Chang'e 5 landing site, in full illumination, we have no indication of water. And this is consistent with measurements on the ground by Chang'e 5 by their ground-based spectrometers. As the eclipse proceeded, a 3-micron band appears in a matter of a few hours, and it disappears when the eclipse is over. So this phenomenon, whatever it's happening, happens at a pretty high speed. There may be a little hysteresis in the data, but we're going to do some more observations in a couple of weeks to try to confirm that. So 2 hypotheses are surviving. One is that this reflects water molecule bouncing around the lunar surface, migrating away from the subsolar point, and then condensing on the, not condensing, but being cold trapped on the cooler portions of the surface. So that near the terminator, all around the moon, the temperatures are lower, so any migrating water will stall there and cause an absorption, whereas at the subsolar point, you won't see an absorption. there's a real problem with this, that the amount of water that we're seeing exchanging with the surface, if we attribute it all to molecular water, puts a ton of water into the exosphere, way over the 1 molecule per cc, which is the upper limit from the LADI mass spectrometer in lunar orbit. The other is a new process where OH, metastable as OH is formed as diffusing hydrogen, which is implanted from the solar wind, hops from oxygen to oxygen on its way out of the soil, and that forms temporary OH bands. And this is a strongly temperature dependent process. It's been recently supported through molecular dynamics, but the actual spectral effect has never been demonstrated in the lab, though Bill Farrell and O.J. Tucker are working on doing that. There is a possible problem that the H supply during an eclipse, which is full moon, the moon is buried in the magnetotail, and the H supply is pretty low, but we'll have to see if they can actually make this happen in the lab. So there's a real mystery here about what is going on with this temperature variable absorption feature. Is it abundance variations of OH, or is it actually migrating water? Both of these hypotheses imply there should be basically no water in the background soil. This is an exogenous process, or exogenous in the sense that it either needs solar wind or it needs migrating water. Okay, so what do samples tell us about the background water abundance? I know you guys measure at the sort of nanoscale, but we're talking about the bulk scale. So Matt Izawa at University of Winnipeg, at the Ed Clutis lab, requested samples a few years ago. They took heroic measures to make sure that the samples that arrived at their lab were not contaminated with Canadian water, wisely enough. And they measured with an infrared spectrometer a 3 micron absorption feature. So on this axis here, which is horribly mislabeled. Is it mislabeled? No, that's just my eyes are horribly blurry. This feature that sort of rises up to about 2.8 microns and it falls and is very broad is indicative of the presence of molecular water in the samples. And they saw it in all the samples from all the sites. Now, recently, Ryan and Juliana were talking about this, and they had their staff go back into the samples and see if there was any evidence of exposure of some of these samples. And it looks like at least some of these samples were definitely exposed to terrestrial water before they went into curation, either in the crew cabin or in the spacecraft in the water in the Pacific. Okay, so at least some of these samples seem to be contaminated. They all kind of look the same. So there's a good chance they were all contaminated. So when we've been doing our measurements of the multispectral experiments, we have been talking about measuring samples after they came out of the pristine cabinet and trying to do this experiment and trying to control this atmospheric contamination problem. And Ryan suggested that since after the last pass had been done and the core was going to be taken out for epoxy impregnation, we could put our spectrometer in the pristine cabinet while it's still purged with dry nitrogen and try to do this experiment before the samples were handled. So this is the epoxy pore part of the core that we were dealing with. So here's what it looks like. So this is the infrared spectrum. Well, the TV land can't see this. So there's an image on the right. There's a white box. This is inside the pristine cabinet. The white box is an FTIR that operates from about 2 microns out to 14 microns. There's a fold mirror that looks down at the core. The core is in the bottom right. There's a lamp that illuminates the core. So these are all in reflectance. And it's the same spectrometer that Matt Izawa used. Not the same one, same model that they used in Winnipeg. Okay. So we outgassed the spectrometer in the nitrogen purged airlock overnight. We collected data at several spots along the core. Clast had been plucked out of this last pass. We measured flat areas in between the little craters left from the class. We measured the core in the afternoon, returned the next morning to repeat the measurements. Then we vented the cabinet and then collected data 2 hours later to see the effect of terrestrial water. So what did we find? So the spectrum on the top is kind of the punchline. These are like the Ozawa spectrum, same instrument, same all of that. We see no evidence of a strong water absorption in the background soil.
2-minute warning.
Thank you. There's a little bit of noise on that data. We're working on this, but the sort of sensitivity limit's about 50 ppm. When we came back the next day, a water absorption had appeared. We may have brought water in the cabinet, still outgassing from the spectrometer, and also the nitrogen bottle may have had a little bit of condensation on it when it went into the cabinet. It warmed up and could have released water in the cabinet. So after 18 hours, we saw a feature appear. Then after the venting, after a couple of hours, we see kind of an ordinary adsorbed water feature. And for reference, this is a soil 63221. It has terrestrial water contamination. Should have put a Mare soil. It looks more like the day 2 after venting. Okay, so include, so the lunar background regolith does not appear to contain adsorbed water, and by meaning adsorbed water or hydroxyl. This is consistent with remote sensing of surfaces at the higher temperatures. It permits both of the viable hypotheses, but doesn't add any discrimination to either one. We'd like to confirm this using the core samples that were actually obtained. They should be water-free, and we'd like to measure them both at Winnipeg and in Hawaii. And we want to extend our wavelength region out to 6 microns so that we can actually detect the presence of molecular water versus hydroxyl. Thank you.